Today we're going to cover the concepts of the error correction criteria for quantum codes. And the way I'd like to do that is to begin with a brief review of what we have learned for classical coding and quantum coding, so that I can tie all these threads together and use a single piece of language to describe the entire set of concepts and field. And so I'll rapidly move from classical to quantum using the same examples that you have seen. Then I will introduce a new terminology, a new mechanism known as operator measurement. And using operator measurement, we'll be able to see an operationalized version of syndrome measurement, and then the step after syndrome measurement, which you haven't explicitly seen so far, which is something called the recovery operation. And then based on that recovery operation, we'll be able to formalize what the criteria are for when you can correct errors and when you cannot correct errors. And this is a beautiful, phenomenal thing to know about in quantum error correction. Questions before I go on? Okay, so let's begin with a little bit of review. You may remember that the scenario for the classical coding began with this notion of having a noisy channel. And the noisy channel was one in which you would have an input 0 that would stay 0 with a certain probability 1 minus p. But with a probability of error p, the 0 would turn into a 1, and this was symmetric, so that a 1 could turn into a 0 or stay unchanged with the same probability of error. So p is the probability of error. Now, this is called the binary symmetric channel. And we apply the binary symmetric channel to a variety of codes. And then we show that by doing something basic, which was repetition, we were able to correct for this kind of error and other kinds of errors. And this is also known as a bit flip error when you have a 0 going to a 1 and vice versa. So what we did not do was to define what a classical code was. And I'd like to summarize that for you right now. Let me define a classical code. With some parameters, n, k, and d. And this will be a very simple conceptual definition. This is exceedingly general. It's not meant to actually be very useful. And the reason I give you this kind of definition is because I want you to see the parallel of this definition with the quantum version of it. So a classical NKD code with 3 parameters is defined as a set of 2 to the k n bit strings in the set of all binary strings with a certain property with minimum Hamming distance between any code words in this set of bit strings d. So I'm not implying any structure on this set of bit strings. For it to be a code, you don't have to have that structure. But remember that what you saw in lecture was Professor Shore giving you a very special set of such bit strings which were generated by a matrix, a generator matrix, and these were called linear classical codes. And it's very nice to have families of codes like that, but just for the definition of what a code is in principle, you don't need to have that kind of a specific definition. So in order to use this definition, one thing we need is the Hamming distance. And I want to make sure you all remember this. The Hamming distance d between 2 code words x and y is the weight of x plus y, where this is the Hamming weight. That's the number of 1s. And this here is a bitwise exclusive OR between the 2 strings x and y. And for linear codes, when Professor Shore described this, there was just an addition sign there. And what he meant was for it to be modulo 2 in the sum. And when you're using general bit string codes like I have here, this is the more general way to look at it. So let's give an example. Suppose I encode with 3 zeros as being a representation of the logical 0, and 3 ones as being the representation of a logical 1. What are n, k, and d? Anyone? N is equal to, this is an easy one. 3, okay. What's k? I heard somebody say 2 though. So you can see that the reason it's 1 is because there's only 1 bit encoded using 3 bits. Now what is d? 3. And why is it 3? It's because you need to flip 3 bits to go from one word to the other word, and there are only 2 words here in the code space.